everybody in person and how many online?
We have one right now.
All right, welcome to our one online attendee.
They trickle in.
Okay, yeah. Welcome to the basement of Farrell Hall, home of the Water Resources Institute at UVM. I'm Keith Jennings, I'm the Director of Research. Some of you I've met, some of you I haven't. I'm not going to take much time up here because we've got an excellent presentation coming from Brian in just a few minutes. And I want to really hand over to Hannah Fisher, our Communications and Events Manager, who has pulled this seminar series together. And she'll introduce how it's going to work for the semester and some of the things we're going to talk about and learn about over the coming semester. Yeah, Hannah, you take over.
Okay, the second introduction. All right, so as Keith said, I'm Hannah and I planned this series. And this series is our second in our Water Connects, which we run every fall, and we feature research around campus. And this one is specifically on the implications of health and water in regards to both like stream health and ecosystem health, as well as human health. So we typically do a 30-minute presentation with snacks and food, and then we offer time for questions and discussion at the end. And with that, I'll introduce Merce, who's going to introduce Brian.
Okay, so mine will be less flowy. So I'm going to read a little bit about this. So hello everyone, and welcome to the first presentation in the Water Resources Institute's Water Connects Water and Health Seminar Series. So as Hannah said, during this seminar series, we are looking to highlight research on connections between water and health. My name is Merce Morales. I'm a postdoc here at the UVM, and I'm very excited to introduce today's talk by Brian Ebel with the USGS entitled Potential Interactions of Wildfire and Historical Mining in the Western United States, Implications for Stream Water Quality. So a little bit about Brian. Brian Ebel is a hydrologist at the US Geological Survey who uses field measurements combined with numerical modeling to advance prediction and assessment for water resources to improve process representation. His work focuses on landscape disturbance impacts like wildfire, forestry, and legacy mining, on water availability and water-related hazards to human lives and infrastructure. Currently, his research focuses on managing 14 post-wildfire water quality observation sites, including scientific analysis and model prototype. Brian currently sits in Farrell Hall in that office in the UVM Water Resources Institute and has an adjunct appointment through the UVM Department of Civil and Environmental Engineering. So as Hannah mentioned, this is going to be a talk of 30 minutes with 15 minutes of Q&A at the end. So please hold your questions until the end, and welcome to our one remote guest, or maybe more. And yes, now I will turn the floor over to Brian.
Thank you.
Thank you, Keith, Hannah, and Merce. I appreciate the opportunity to speak today. I want to extend a huge thank you to the UVM WRI for the opportunity to have office space here in Farrell Hall, and especially to Beverly and Josh for making that happen. I also want to thank the UVM Department of Civil and Environmental Engineering for considering me for an adjunct position, and I look forward to building interactions with UVM faculty and staff. So a little bit of background, I'm a physical hydrologist. I work on fluxes and stores of water as it relates to water supply and natural hazards. And most of my work is centered on landscape disturbances and how they change hydrologic processes. And in the last few years, I've been working increasingly with water quality experts to understand how landscape disturbance changes hydrology, which in turn propagates into water quality. And that's what I'm going to talk about today. So there's a huge spectrum of landscape disturbances, everything from discrete events, what we would call pulse disturbances, things like fire, to longer lasting disturbances, things like decadal droughts that extend over longer periods. And while we tend to think of these disturbances in isolation, it's increasingly recognized that they overlap in space and time. That is the rule rather than the exception. And when these disturbances interact together, they can compound in important ways. And I'll talk about 3 examples of that. So one example would be what I'll call amplification, which is that in this case, this is a wildfire that has interacted with an atmospheric river, and we've greatly amplified, in this case, a debris flow response. We see that in water quality also. So in some cases that increase, that compounding can be additive or it can be nonlinear, meaning you might get hundreds or even thousands of times the response. You can see expansion, which is a sort of an extent both in spatial and time reach. So we can see expansion beyond the reach of either disturbance alone. So for example, downstream propagation by many kilometers, or you can see an increase in duration. So going from something that might be a fairly short duration to extending for months or longer. Another example would be diversification. So the example shown here is suburban development that has encroached against a wildfire area, and that's typically called the wild and urban interface. And so now we have combustion of all of these built materials. And so instead of having the typical water quality response of wildfire or suburban development alone, we've introduced this whole new suite of potential water quality constituents to be concerned about. And that would be called diversification. And in some cases, you can have interaction, and people talk about chemical mixtures or chemical cocktails or degradants. Now, there's a seemingly infinite combination of disturbances, but I'm going to focus today on two, which are wildfire and mining. And the work that I'm going to describe today is in what I would call the reconnaissance phase. After decades of research, the community understands numerous wildfire effects on water quality, and I'll go through those in a minute, thinking about kind of fire and isolation. After decades of research, we also understand numerous mining effects on water quality, so thinking about mining and relative isolation, but we're just beginning to understand how these intersect and interact, and trying to figure out where, meaning both regionally, where are there problems, and also within a specific watershed. So where are going to be the hotspots or problems of water quality response? Also thinking about the what, meaning which metals should we look for? What metals are going to be problematic in both dissolved and solid forms? And how? So which processes are going to be most important, and at what timescales are they going to be important? And I'm going to kind of run through all of those today. But I have to admit, I don't have kind of this final, really conclusive result yet, just because that's the phase that this work is at. And also there's some data set challenges that I'm going to delve into that I think are going to be resolved in the next year or so. I'm going to start talking about wildfire. And so this animation will step through the burned acreage by year from a geospatial data set that's from satellites, specifically from Landsat. From the monitoring trends in burn severity, or MTBS. On the left side of this graph will be the acres burned in these 11 Western states that are shown on the right. We'll step through in time. On the right, we'll show cumulative burned area. So it'll be from 1984 through 2024, and it's going to add up each year as it goes through. So you can see there's a lot of interannual variability in the area burned. There are years where there's a lot of fire in the landscape and years where there's less. But you can see that over time in the graph on the right, we're over the last 40 years really beginning to burn a substantial area of the Western US as the landscape adjusts to decades of fire suppression. The topic of this whole seminar series is health effects, and wildfires just on their own can have substantial health effects. If you live in the Northeast and you spend time here this summer, you experience some of that with some of the particulate effects from fire. On the upper right is upper left is the fire and smoke map from Air Now. And so those effects can be both localized. You can see some of those yellow and orange areas that are from local areas of wildfire smoke, but they can be regional when that smoke is atmospherically distributed, and you can get particulate health issues. You look in that photo in the center, that is a burned home in Colorado. A colleague of mine lost their home in a fire. And when we burn constructed materials that can introduce a host of health issues in the environment. There was an entire National Academy's consensus report that summarizes some of those, sort of the chemistry and associated health effects of those. But where I mostly work is in that lower left corner, so the intersection of wildfire and water and fire effects on water quality specifically. So I'm going to kind of briefly step through why there are these fire effects on water quality. And I'll start with the physical hydrology changes that happen after fire. The cartoon on the left is this kind of before fire picture. We'll have a closed or nearly closed canopy forest. If we would zoom in to where that little blue box is, you'll see at the soil level before the fire, we'll typically have several centimeters of litter and duff, what I would call necromass, which is just dead vegetative material like needles and little branches. Some of that's going to be incorporated into the near surface of the soil in this organic rich layer. So this is this nice fluffy forest soil that we're used to. I could walk out here and pour a bucket of water on the ground and it would infiltrate very rapidly and probably all go in within a few feet. Now, the effect of the fire, specifically in the case of moderate to severe fire, which means fire that consumes a lot of organic matter, both above and below the ground, can produce some major changes in hydrology. There's what's called interception, which as a hydrologist, you're probably familiar with. That is water that is temporarily stored in the vegetation canopy. Depending on the phase, it is either evaporated or sublimated back into the atmosphere, so it doesn't reach the surface. We've defoliated a lot of the canopy, the interception is gone, there's a lot more rainfall hitting the ground. There's also, water can be stored temporarily in litter and duff. If you've combusted a lot of that, that is also removed. So a lot more water hitting the land surface. Because of the heat of the fire, we can heat and degrade or even combust the organic material in the soil, causing the soil to collapse. So we've lost storage in the soil. We can also substantially change infiltration rates. After the fire, the combustion of all of the vegetation material and the litter can introduce ash. Ash is typically very fine grained. It can clog pores in the surface and reduce infiltration. It can cause surface sealing from fine soil and ash. And so a lot of those factors reduce the ability of the water to enter the soil. You can also have what's called water repellency. So all of that organic material contains these waxy organic substances. When they're heated, they can volatilize and then they can recondense on the grains of the soil. It's like, it can be like melting a candle on the surface. The water just simply cannot enter the ground. It doesn't wet the soil. From that heating, you can also have structure loss. So the soil can collapse. The largest pores conduct the bulk of the water in porous media. And so when we collapse that soil, we greatly reduce the hydraulic conductivity. All of these factors act to basically mean that we've got a lot more water falling and reaching the surface and a lot less going in. And that's important for runoff generation. So before the fire, most stream flow at the storm time scale would be generated by what's called subsurface storm flow. So it would rain, the water would mostly pretty much all go into the ground and it would slowly wet up. So there's lots of storage in the soil. Eventually we would generate saturation at that soil bedrock interface, and that water would flow downslope relatively slowly through the soil. So we've stored a lot of the rainfall and we're smearing it out in time because it's slow through the subsurface. That's because the rainfall rate is much less than the infiltration rate. Because of the factors that I've talked about, we've got a lot more rainfall coming down and we've got a lot more going in. And so we flipped that equation. We've got rainfall rate much greater than infiltration rate. Now when it rains, very quickly we have saturation at the surface, lots of overland flow, and very minimal penetration to the wetting front. And so we have lost all of that storage in the subsurface, and we've got much faster storm flow generation because the water is flowing over the land instead of flowing through that soil. And that has important consequences. We typically see very large increases in surface runoff and substantial post-fire floods. And if you get enough sediment and terrain, you can get what's called a debris flow, which is a very destructive mud flow type situation. So I'd like to show an example of one of these flash floods. This is after the 2016 Spring Creek fire in Colorado. This is the first frame of this movie. You can see some boulders there in the center. You can see some woody debris that's wrapped around that telephone pole. You can see there's a bit of a remnant of a culvert right here. So this was a road that's already been washed out. And so you can already get a sense of the flow. This is well outside of the bank. This is a pretty substantial flood, and I'll start the movie. You can get a sense of the reach of this. You can see that chocolate milk color, tons of suspended sediment, amazingly high turbidity. As this pans around, you'll see some homes that have been endangered and some outbuildings. Another important thing to notice is that the vegetation is green. This is not burned. The fire is way up in the headwaters, and this is kilometers downstream. And so you get a sense of the spatial reach of some of these events. So they're affecting downstream transportation infrastructure, homes, reservoirs. You get a sense of the destructive nature of those flows. And there's numerous water quality effects. You could see from that chocolate milk color, there's a lot of suspended sediment. really high turbidity. The turbidity can pose problems for water treatment. There's elevated nutrient fluxes like carbon, nitrogen, and phosphorus. There's altered organic carbon characteristics that affect water treatment. And then there's a few other things that are less substantially studied and can vary a lot. Things like increased metals and polycyclic aromatic hydrocarbons. Put a pin in the metals piece because I'm going to come back to that in just a second. So I talked about how these overlapping disturbances are the rule rather than the exception, and the Western US is definitely no exception to that. There's a lot of historical mining in the Western US. And by historical mining, I'm talking 1800s through mid-20th century. Some examples of that, this is an ore processing facility in Creed. You can see there's a person for scale. This is pretty large scale mining. There's a hydraulic mine in the center from Placer County. You can see there's a person for scale. So these are huge deposits, really large scale disturbances. But there's also a lot of small scale mining. On the right is a small scale mine in Leadville, Colorado. Mining has pretty well established effects on water quality and health. There's a number of metal sources. There's mine drainage in the subsurface. There's hill slope erosion and transport of mine waste and tailings. Those materials from the hill slopes can be pushed down into floodplains and stored in channels. They can also be transported in the dissolved phase through groundwater and hyporheic flow. It's been estimated from this Macklin paper et al. In 2023 in Science that in North America alone, over 200,000 kilometers of river reach and 40,000 square kilometers of floodplains have been affected by historical mining. So this is a pretty pervasive disturbance in the Western US. And there's a number of health effects from mining that are pretty well established, like dissolved metals in water bodies, plant, crop, and animal product contamination from soil. So plants can take up metals from soil and also from irrigation water. And then if animals eat those plants, they can then have those metals incorporated into themselves. You can also have bioaccumulation through fish and shellfish. If you go around the Western US, you see that a lot of these areas that were mined, over 100 years ago have revegetated. And here's an example of that from the Yankee Girl mine, which was founded in 1888. It's a silver mine. It's near the aptly named Silverton, Colorado. That's Red Mountain, if you've ever been to this area. And if you look at this photograph, you'll see that there's a lot of mine workings. There's a lot of piles of mine waste, tailings. Not a lot of trees, and that's because there's a lot of forestry associated with building the mine workings. There was also a wildfire here in 1897 that basically destroyed all of the mine workings. And so they had to rebuild a lot of that. So the fire plus the mining actually defoliated a lot of that area. And in the intervening 100+ years, there's been a huge amount of revegetation. So there's been tree growth over a lot of this, and you can see that in that right photograph. This is a pretty ubiquitous situation throughout the Western US. Some other photos from Montana and Colorado. In the photo in Colorado, all those little kind of pale tan areas are revegetated mine waste piles. There's a lot of potential mine sources when you have this intersection of wildfire and mining, and I'll step through this kind of relatively complicated diagram. It's a mixture of sort of this cartoon plus some photographs. I mentioned that vegetation can uptake metals from soil, and then when you burn that vegetation, you can re-release those metals out into the system, and they can be entrained in ash and transported into water bodies. That's shown in that little number 1. You also have a lot of superficial legacy waste, so tailings and waste rock. That can be eroded by flash floods and debris flows. That's shown in number 2, or here's a photograph from near Boulder, Colorado, where that was eroded through those piles of tailings and then transported into a stream system. You can have tailings ponds, that's shown here in 3, and also in this photograph, C on the right. Those could potentially be breached by some of those flood type flows that I showed in that movie. Underground mine workings. So you have a lot of tunnels and adits. Water can flow through those underground mine workings, either as groundwater flow or as flow that flows through the tunnels and then emerges, where it can either flow into systems or even erode tailings piles, depending on the strength of the flow. You can have floodplain sediment that was deposited from, say, mining that's then eroded by flood flows after the fire. And so that can be either stripping of floodplain sediments from a stream avulsion, or it could be a failure of bank material that's then entrained into the stream. You can also have deposition. So it's possible that that flood flow could be carrying a lot of mining sediment, and then it could breach the channel and then come out and be deposited in the floodplain where it could be remobilized by a subsequent flood. You can also have hyporheic or groundwater flow. So you can have flow in and out of the bed where there might be relic mining sediments and then fire sediment on top. So you can have an interaction of the fire and mining geochemistry through flow that goes in and out of the bed, or you could have flow that enters through the bed through a groundwater system. And that could also potentially happen in a reservoir setting. So there's a huge number of potential pathways for metals in this system. So, let me go back. So one of the challenges here is if you want to try to figure out where in the landscape this is going to happen, you have to know where all of these piles are. That is a huge challenge. And so I'm going to talk about that historical mine feature data sets. So if you've ever looked at a USGS topographic map, there are all of these little symbols that denote, oh, here's a mine shaft, or here's a tailings pile. And those are mapped out all across the US in a data set called USMIN. And that's probably the most authoritative mine data source that's available at a national level. There is a separate data set that has a long history. It's started out there, what's called MRDS, which is the Mineral Resources Data System. There used to be a US Bureau of Mines that maintained 2 different mining systems. The US Bureau of Mines was closed down in the 90s, and then the USGS took over the Bureau of Mines systems along with its own system. And as you might imagine, mining has been going on for over 100 years. So a lot of these maps predate the digital era. And so there's lots of potential errors in digitization, in propagation, in merging these 3 different data sets. And so at the moment, the USGS is merging these and trying to build a merge system that has both the mine symbol data from the topographic maps and then also that mineral deposit data. Both of these are important because the mine symbol data is more geospatially accurate, but the mineral resources data contains the commodities. And I'm going to talk in a minute for why the commodities are really critical. So the first question we had is, how pervasive is this across the Western US? And so here's just a pretty simple geospatial overlay of fires over about the last 40 years. And then the black shows the prospect pits or mines, the little black dots. And those are from USMIN. I've also shown you the MRDS data set also. And so if you look at that graph, the cumulative fire affected mining sites with time, there are tens of thousands of cumulative potentially mine sites that have been affected by fire. And they track pretty well with fire. So the wildfire line is that orange line in millions of acres. And so as fire increases on the landscape, especially in the Western US, we are going to continually potentially affect these mining sites. A lot of these fire and mining sites overlap with potential surface water supplies. So this is a map of an assessment that was done by the Forest Service, where they looked at different watersheds and their importance to surface drinking water supplies. And they color-coded them sort of for low importance is the really light blue, and then the deeper blue is where they're really important to surface water supplies for communities. And so you can see there's a lot of intersection, especially in California, but also in Arizona and to some extent Colorado, between wildfire, historical mining, and important water supplies. And it's not just in the past. So if we look at fire assessments of where there's moderate to very high fire potential, as shown by that red shading, a lot of these watersheds are also in areas that are really prone to being burned in the future. They have high fuel loads and they have climatologies that are conducive to burning. So this is a potential future problem as well. If we look at the kind of the intersection of the fire areas with where there are historical mining sites, and we look at what has been affected by fire. So this is just a count of all the sites over the last 40 years. and what type of mine feature they are. So prospects are these kind of small scale features. Adits are usually like the mine shafts that you see. And a lot of what we think about when we think about fire sites are these big sites, these big open pit mines, or these big, like mineral processing facilities. Those are a tiny fraction of fire affected mine sites. And really, most of the sites are these little sites that are distributed all across the landscape. And so if you're thinking about where are the potentially exposed sites and where are the metal sources, it's really a lot of these little places that have little sites that have revegetated in the period since there was fire. The graph on the right shows the count of these fire affected mine features by the fire size. So these fractions are pretty consistent across fire size. There's a little, you do get kind of towards the right end, the bigger fires, there's a little bit of a shift towards some of those larger features, like the pit mines, but it's mostly going to be prospects and adits and shafts. And here's where we get into some of these data set challenges. So if we look at the total over the last 40 years from these two different data sets, USMIN, which is from the topographic maps, and MRDS, which is from those merged minerals data sets, I've got the state here on the left. I've got how many fire affected mining sites are in each state, and then on the percentage of the total. And then on the right, I've got the size rank, so just by area. And you can see that Nevada is the 5th largest state by area, but it has 40% of the fire affected mining sites. So it sort of punches above its weight in terms of fire affected mining sites. California is #1 in size, and it's got about 19%. And some of these other states like Idaho and Utah have I would say, a disproportionate number of affected sites relative to their area. On the right, it's a pretty different story. We have very different states that are affected. California is far and away the most affected state. These differences reflect that there are state level data sets of these mines, and some of those have been better incorporated, or maybe more heavily weighted is a better way of saying it, into MRDS. And so there's an ongoing effort to merge these state data sets with the national data sets to build a comprehensive unified data set, but we're not quite there yet. So the USGS, I believe they're going to finish it within the year. But you have to be careful when using these different data sets and trying to decide where are the where are the most prone states to be concerned about. And the same thing is true if you look by ecoregion. So some of these data set differences propagate into ecoregions, which is an Environmental Protection Agency classification. The main thing that I take away from this is that there are state level differences. So these are Nevada ecoregions and these are California ecoregions. So those are data set differences. But there's a huge diversity in ecoregions here. There's both tree dominated areas like forests, and there's also a lot of shrub dominated areas. And so you need to understand the fire differences in these different vegetation classifications and how that might mobilize mine waste, because there are differences between the two. There's also differences in commodities. So this is fire affected mine features by the original mine commodity. So, and here's the percentage. So really almost all of the mining is gold, silver, and copper. And that's pretty stable across fire size if we look at count of the features across fire size, except on the far right end, the largest fires, we shift to a lot more chromium, and that's because of California. Northern California has more chromium mines. These large fires in California, especially Northern California, is the source of that, I believe. So some of these, reconnaissance level takeaways. There are thousands of historical mine features that are within wildfire perimeters. Prospects and small adits that have revegetated are the most frequently fire affected in the past and likely to be the most frequently fire affected in the future. So even though when we think about mines, we think about these giant pit mines, it's actually the features that are potentially the most important. There's varied ecoregions that are affected, so we can't just focus on forests. We need to think about shrub landscapes also. A lot of the focus is on a few commodities, and so if we understand what those commodities are, we can look for associated metals that weren't the economic commodity that was targeted, but could potentially detrimentally affect ecosystems. There are ongoing mine feature data set challenges, but I think that those will be resolved within the next year, and then we can push forward with a more detailed analysis and getting into things like erosion and mobility proxies to try to understand, okay, here are the sources, but where is it going? And I want to just dive a tiny bit deeper into this piece here to close out. So in mining, they talk about what's called metal companionality, which means that the primary metal commodity can be quantitatively linked with other metals. So the center of this chart is basically what you're originally looking for when you're putting your mine in. It's going to be things like zinc or copper in those dark blue. As you move out away from the center, that's the probability that it's going to be, there's going to be one of these trace elements associated with that commodity. So like for copper, there's extremely high probability that selenium or tellurium would be there, and a very low probability of like iron and mercury. And the reason why this companionality is important is that you can use it to identify other metals to look for. You might be able to use it as a metal fingerprint, meaning that if I know that there's a titanium and a copper mine in a watershed and I'm seeing a ton of selenium, well, it's probably the copper mine that's the source of the metals. You can also potentially use it to identify what are called critical minerals, meaning minerals that are used in supply chains, especially technological supply chains that our nation has some supply challenges at the moment. Some of these critical minerals can be present in economically viable quantities in historical mine waste. And so there's an ongoing effort to think about this mine waste rather than as a problem, but as a resource. So some of these mine wastes contain minerals that are valuable, but were not desired or economically feasible when they were mined, nor they weren't technologically recovered with the mining processing that they had at the time. It's been pretty well established that there are mine waste risks associated with some of these mine wastes. There's a photograph on the right of a tailings deposit that was eroded by a post-fire flood and had to be emergency remediated by the EPA. So removing some of these mine waste deposits and mining them is a way to help reduce that hazard. So it's an opportunity. It's kind of like sort of the bonus. Like you can remediate these potentially problematic deposits while also having them be economically recoverable. And so that there's an ongoing effort to do this with multiple agencies as the website to the QR code if you're interested. So thank you. I appreciate your time. I know this has this sort of reconnaissance level of conclusion. So I appreciate any input or thoughts that you have on some of the next steps once some of these data challenges have been resolved.
Thanks for the talk, Brian. I'm wondering, this is a great overview of the the scope of the data sets and what you're looking at. Are USGS researchers either in your group or elsewhere making connections with the impacts of fire-related water quality challenges with either ecosystem people or human health people to take this stuff to the next level?
Yeah, so there's a mix. There are people in the USGS. So this work was largely from what's called the Environmental Health Program, and so there are folks in there that are doing invertebrate toxicology, and in fact, even at some of the sites that I didn't talk about, they were doing invertebrate recovery from fire, and then some of those sites also had historical mining. So there's been some effort to look at metal concentrations in biota, specifically invertebrates, stream invertebrates. And then also there is an effort that we're trying to get started up for some of the Washington fires. There's a fire in Olympic National Park where there's some historical invertebrate data, and then we're trying to get that re-going. There's a fire that is actually still uncontained in that watershed, and so we'd like to kind of fuse dissolved metals measurements in the stream with some of the biota measurements, and there's also anadromous fish in some of these watersheds, so that gets at some of that accumulation piece. So it's there's not a large integrated effort, but there's some of these kind of piecemeal efforts, and then kind of some future efforts that we're trying to get going. But it's important, yeah, to make that link between the source, and then, you know, sort of where it goes in the stream.
Health implications.
Yeah. We also are working with water providers on some of the other effects like turbidity, specific conductance, nutrients. Separately, I have a large project that looks at post-fire water quality observations that most of the sites don't have mines in them, but a couple of them do.
Have there been any studies on the possible causes of these fires? Could it be related to the mining in particular areas causing a disproportionate distribution in air quality of some sort? And I was wondering whether there was any, that's the base foundation of everything, isn't it?
There are a lot of efforts that look at fire ignitions, specifically whether they're natural or human-induced fire ignitions. I'm not aware of any that are looking specifically at mining. I know there's a lot of historical, you know, like 1800s railroad and mining ignitions, but in the modern era, there's a lot of human ignitions of fires that are more recreation related or arson, unfortunately.
The trees are healthy conifers, and I'm just wondering what it takes for a fire that starts somewhere to expand itself, given we have green, very healthy trees surrounding it, the rate of, I don't know what the official terminology is.
Yeah, that's a good question. There's been a lot of studies around fire, what they term fire weather conditions, which relate to changes in atmospheric conditions that dry out fuels in a way that promotes what they call extreme fire behavior. So rapid fire spread, like long spotting, like fire carrying long distances, along with increases in what they call severity. So, you know, if you would go back sort of in the pre-settlement era, you would have seen, at least in many landscapes, a lot of frequent low severity fire. So ground fire that just creeps along, doesn't kill the trees, just kind of clears out the understory. And in some cases, Native American communities would manage forests that way. They would, you know, manage fire on the landscape to clear out the underbrush because it eased hunting or was useful for agriculture. And so there's kind of this, you know, 20th century fire suppression has really changed a lot of the vegetation in some, not everywhere, but in certain forests. And so part of that increase that I showed in burned area is a landscape scale adjustment to changes in land practice, and largely in the 20th century.
Could you go back to the wheel of compatibility? I've
Sure.
seen that before. I've actually used it in a class, but I can't remember. I mean, is this about like charge and ionic radii, or are these things that tend to occur at the mineral systems level?
Yeah,
together?
it's a good question. I think in some cases it's a mixture of like sort of, you know, metal chemistry, but I also think that there are certain ore bodies and like hydrothermal, you know, whether it's depending on the genesis of the ore body that sort of change. I mean, I think that's part of why there's so much scatter.
Yeah.
There is a recent database that like global database that fuses like sort of geology plus ore body type and genesis with some of these commodities. And so I think that would be helpful for teasing apart some of those relationships.
Just one thought I had was like, if you're thinking about, oh, they're mining gold, and so what's likely to be associated with that? Well, if the gold ore is mainly gone, what's left is the gangue. And so thinking about, or the waste rock.
Sure.
So thinking about what that host.
And it's just hard. I mean, as you know, with gold, there's a huge variety of types of gold deposits. And so that's why I think there's kind of more scatter in this diagram when you synthesize across, you know, sort of ore bodies. You get a little more of that, I don't know what fuzziness. But I think, yeah, if you would distinguish by geology and the type of ore body, I think you would probably have some more definitive separation of that companionality. I think that's a good question. And carbonates, one of my colleagues is, you know, said like, well, you know, whether or not you see, you know, acid mine drainage depends a lot on the, you know, the carbonate content of the host rock. So that's going to change the mobility and, you know, whether it's dissolved or not. So.
Does anyone have any more questions?
Not online. So thank you.
Okay, thank you so much. I appreciate it. If you have, you know, if you think of anything later, feel free to reach out.
Thanks.